how to make a film about CERN.
Well, it seems to me that one of the most difficult things we have to talk about is how actually to put across some of the basic ideas in particle physics that will be necessary to anyone who wants to understand what goes on here at CERN.
What sort of people are you aiming at? What sort of background do these people have?
Varied. I mean, very varied indeed. And for some, a continuing interest in the sciences, sometimes a very well-informed interest, and sometimes not.
Mm-hmm. And are you aiming to tell about particle physics or about particle physicists?
Mainly about particle physics, but incidentally about particle physicists.
Mm-hmm. So then you want a sort of formal lecture where somebody...
No, on the contrary, no.
Somebody starts by telling people that matter is composed of small pieces, and these small pieces are composed of still smaller pieces, and so on. Now, the atom is something that you can describe to people, because that's like the planetary system.
Yes.
There is a center, and there are a number of electrons going around this center, which is the nucleus. And it seems to me that that's... you can tell people that. That's nothing strange about that, except the scale, that it is very small.
But as soon as you delve deeper into the atom, things get stranger.
So the condition for a theory in which the infinities can be handled at all, a necessary condition is that the coupling constant has a dimensionality which is positive or zero. The coupling constant appears in the Lagrangian multiplying some kind of operator.
Hidden within the maze of mathematics were the descriptions of an array of subatomic particles no one had ever seen before.
Cheers to the W.
To detect these particles, scientists built increasingly bigger and better accelerators.
It's getting 100 times the energies they've got now, but it will be exciting. But there have been tremendous advances in theoretical physics, in particle physics, since I came.
And what gradually emerged from these atom-smashing experiments was a detailed picture of the very early universe. By the 1980s, particle accelerators were so powerful that they allowed scientists to catch a glimpse of what our universe looked like just moments after the Big Bang. Although great strides had been made by the particle physicists, the irritating fact remained that even with the mysterious dark matter that nobody could find, the Big Bang just didn't work without the ripples in the Penzias and Wilson cosmic background radiation, the telltale patches of hot and cold that the U-2 spy plane had failed to detect. In a last desperate attempt to find the all-important ripples, a satellite called COBE was going to be launched on board a space shuttle in 1988. But on the 28th of January 1986, the entire project was thrown into jeopardy. The Challenger disaster meant that NASA had to reassess its whole space shuttle strategy, and before long, COBE was dropped from the program. The COBE team were forced to find a substitute launch vehicle, and at last managed to get the satellite off the ground in 1989.
3, 2, we have main engine and the Cosmic Observation Background Explorer. And the vehicle has cleared the tower.
And when its data eventually trickled back to Earth, there was finally cause for celebration.
This is the eve of the anniversary of COBE's launch, the third anniversary, and we're taking time out from the hard work to celebrate this great event. COBE is still gathering data. You see the infrared universe here with some stars in our galaxy showing up. 300,000 years after the Big Bang.
When we launched the COBE, we thought it would only go maybe a year. That was what the original plan was, but we all hoped that it would go longer. So we're now actually in the third year and hoping to run successfully to the end of the fourth year.
Their first results had been faint and difficult to interpret, but with an analytical team that's grown to 100, they now seem far more confident.
Here's the galaxy, and there's the middle of our galaxy. And there's something else here. This part of the sky is much brighter than this part of the sky here. Much brighter means 1 part in 1,000 to us, and it's not really very much. But this is due to the motion of the Earth relative to the rest of the universe. Now, our data processing has actually proceeded to where we can subtract this part out. We can subtract out the emissions from our own galaxy across the middle, and we can deduce the part that's really cosmic.
The remaining tiny fluctuations compete with noise from the detector itself. It takes time to extract a signal from the noise.
We started out the COBE knowing that no one knew how these giant structures and clumpiness could occur.
There's still no complete theory of how this clumpiness emerged and what it means, but at least they do have data for theorists to work on.
This is a map of the universe as it was 300,000 years after the primeval